In the previous video, I got as far as explaining up to a basic active cascade filter. In this next video, though, I would like to talk about different topologies of filters and how they work. So, as already mentioned, this is a cascade filter. So the one on this half of the page, that is set up as a low-pass filter, which, if you remember, has the input signal going through a resistor with a capacitor going to ground. This is one of the most basic and easiest to follow filters due to minimal components used and just a very simple structure. The other main filter I looked at was a ladder filter, and this refers to using several components of a specific type running in series with then capacitors at the junction where they meet. So in this case, this is a diode ladder filter where you have the ladder, as it's referred to here, with your diodes and then capacitors at the junctions tying it to ground. The way that a ladder filter differs from a cascade filter is you have to create a bias signal so you can pass your original signal through the diodes. So I'll explain that here quickly. To explain that, though, I'll have to explain some slight things about diodes. So on this graph, we'll have current on the y-axis and voltage on the x-axis. Now, a basic rectifier diode has an activation voltage of about 0.7 volts. So we'll place that here. And that basically means that across the diode, like this, you need a potential difference of 0.7 volts before it starts conducting. So that would look something like this. And it is very important to note here that diodes are an analog component. They are not digital. So when that 0.7 volts is reached, it doesn't mean that they suddenly let all the current through. It's a more gradual curve. So at this point here, let's say this is 1 volt, you would have this much current able to pass through, which, using the equations for current and voltage, so your voltage is your current times your resistance. In this case, the gradient of this line is 1 over your resistance, as you are dividing current by voltage rather than voltage by current. So this basically means that as you increase this voltage over your diodes, there is a reduction in the resistance. So you end up with a more open diode. And because you are therefore reducing the actual resistance here, you can then take that back to the structure of a cascade filter, whereby increasing the resistance, you are moving the cutoff point further along in its desired direction. So either high pass or low pass. But in order to get that 0.7 volts, because we would be dealing with an alternating current, which swings around 0 volts, and let's say +5 and -5 volts, and we'll go with just a square wave oscillation again, then that would mean that this top half of our signal could pass through, but this bottom half would be cut off. So you would end up with your signal looking something like this, that is actually passing through the filter. Which, as you can see, is only half of the original signal. So in order to make it so we can pass our whole signal through the actual diode ladder, we need to adjust how it is being connected, because if we just had the input at the top of the ladder going through it all down to then ground at the bottom, we would only be getting this top half. So we have to bias it. And in order to bias it, the most obvious solution would be to add a DC offset. So instead of our signal as we had it here oscillating around 0 volts, we'd have it oscillating around 5 volts, and then its peak would be 10 and its troughs would be 0 volts, which again is not ideal because that is your ground connection. So the way you would want it to oscillate is you would still have your input signal coming into the original circuit oscillating around 0 volts, but once it is actually in the circuit, you modify it slightly, but in two separate ways. So let's say this is still between 5 volts and minus 5 volts. What we would do is, as I just showed there, you'd add a positive DC offset. So you would have that around about here. And let's say that one's peak is 10 volts. We would then want a negative offset as well, though. So you're splitting this original signal down two paths and adding your offset there. And then if we say the troughs of this one are minus 10 volts. So that means that on average, with a 5 volt oscillation each way, we are getting a bias between these two signals of 15 volts. Which is more than enough to correctly bias these diodes. Because when you run diodes in series, instead of just having the original 0.7 volts, or this 0.7 volts applies for each diode. So the more that you have running in series, the more this voltage increases. So if you start with one and then you add another, that would then have an activation voltage of 1.4 volts. So by adding more diodes, which increases the order of the filter, you are then also requiring a larger bias voltage. And if you make it so you can adjust the bias voltage, so the width between these 2 points here, you can then change the effective resistance of your diodes as I'd shown on this graph. Because you're changing the voltage across the diodes, you're getting a different point on this curve, allowing your filter to have different cutoff points. And that's exactly what this circuit here does. You have your input signal coming in over here, where it is then split into two different op amps, which are set up in a way to add an offset voltage from one single supply, which you can then add more, or which you can adjust the actual voltage you are applying here to. So that's just set up between plus and minus 12 volts on a potentiometer, And then you can also very easily add an input signal to also control the filter. So that could just be any other oscillation. And it's important to note as well that that is a much more efficient way of controlling a filter than in a cascade filter, because as I said in the last video, these have to change their resistance at the same rate, otherwise you don't get an even cutoff curve. But there is a slight way to get around it, and that's using something called a Vactrol. And a Vactrol, it uses LEDs and light-dependent resistors. So you would have your LED next to an LDR, or light-dependent resistor, because with an LDR, as light increases, its resistance decreases, I believe. And you'll have to excuse me, I can't remember the symbol for an LDR off the top of my head, so I'm just using a general component symbol. So these two circuits would then be completely isolated from each other, electronically anyways, but because you have this connection between the LED and the LDR, you can control different values in this separate circuit. However, there is an issue with this because LDRs can be very slow to activate just due to how they work. And there's not really much you can do around that other than getting extremely high quality LDRs or Vactrols, but they can get very expensive very quickly as they're a very niche component and they aren't used overly commonly in the world of electronics. But this brings me back to the diode ladder here, because this uses something called voltage control, or CV for short. And CV is used massively across mainly analog synthesizers. The other form for digital synthesizers is MIDI. But control voltage is very useful as it's all analog, and you can use it to connect several things all at once and control them off of one single signal, which is the main advantage of doing it using CV rather than Vactrols. However, there are different types of ladders you can make. So this is a diode ladder filter designed by Moritz Klein, and you'll have to excuse pronunciation. But there are other types of ladder filters as well. One of the most popular ones is the transistor ladder filter designed by Moog. I didn't look into it for my project, as I knew from prior knowledge that you have to use matched transistor pairs for the transistors, which can be quite a hassle to either buy or find from your own transistors. So I chose to stay to more regular components such as diodes. So whilst it is a very key example to note, I didn't look into it personally. The other thing to note as well is, whilst these filters do the same thing, they do sound tonally different, especially the resonance. With the resonance path on a cascade filter, due to you having to not bias the input signals or anything like that, you can essentially just take the resonance out from the point and the input, and you can pass it through any effects you like. So you could pass it through distortion or reverb or anything like that. And that's actually what Korg do in their quite famous MS-20 filter, because a common issue with a filter like this is when you turn the resonance up, it can get to the point where it starts oscillating by itself, and that can be very hard to then stop once it starts. So Korg got around this by placing a set of clipping diodes in this part of the amplifier for the resonance, and that would limit the actual volume or amplitude of the resonance coming back into the signal, which would give it... I'll just draw this out quickly. So rather than having the normal sine wave resonance like that, the diodes would clip this signal, giving it more of that sort of look, where you can see that it's clipped at the top and it limits it to a set amount. And that gives quite a unique and recognizable sound to the MS-20 filter. Whereas then ladder filters, specifically the Moog transistor filter, is very well known for how smooth it sounds. And that's, again, down to how the resistance in a diode changes, because it's this nice exponential curve. So by increasing the voltage by a little amount, you get, or exponential and logarithmic, they're kind of interchangeable, but it's a logarithmic curve, whereas this would be slightly more linear. And this can be very handy with this because it makes the filter much more expressionate or musical sounding, and it makes ladder filters much more favorable. However, you are also then very limited with what you can do for the resonance, as you have to be aware of it needing to be biased. However, you can adjust the how you handle the resonance in a ladder filter, and that's what I planned to do further on, which I'll get to in another video. But I think that just about concludes everything for this video. So thank you for watching.